Thank you, Kara. I promise,
Very
I'm
short
an
introduction.
experimentalist, and it's after dinner. Everything I say is really easy to digest. And I know it's between you and sleep. Maybe it's boring, I don't know. But okay. So I want to tell you about X-ray science at ultra-high intensity. And I want to tell you about this. Well, it's a bit weak, like everybody at the end of the day. Because, you know, there are a bunch of new light sources that operate in the X-ray regime that have a trillion times more intensity than those that have previously been around. And so it's really quite a different regime that we've been hearing about for the entire day. so you know, it's something different for you to think about. I have a feeling that probably no one in this room thinks about this except for me. But okay, you know, I'm an experimentalist. You're here. You're supposed to talk to me because you're all there, so you're going to tell me what, you know, how to think about things and how to do them. Okay, so but I'm from Argonne. What's happening here? Okay, sorry. I don't want to go through all this. And when I showed it on my slide, it of course just appears all the way. But go back. No. Okay. But I'm from Argonne, and there are two big, Argonne National Labs outside Chicago, and there are two big things at Argonne. One of the big things at Argonne is that they have a synchrotron light source, an X-ray light source, that feeds about 100 experiments simultaneously. It was previously the brightest X-ray light source around before these yellows. And a dominant theme at this light source is structural biology and X-rays. And to me, it's totally amazing how much X-rays have contributed to structural biology over the years. You may not realize this, but, well, you would if you were at Argonne and heard about X-rays every day of your life. But the very first Nobel Prize was awarded to William Röntgen, and he did structural biology. He took this photograph of his wife's hand with a ring on it in 1895, and 6 years later, he was awarded the very first Nobel Prize. And then shortly thereafter, 15 years later, Max von Laue made the first discovery of diffraction-like X-rays, and it was followed by Bragg's determining the first crystal structure and, you know, the famous Bragg equation, right? So these are all these different things. What you may not realize is that all these other things on this list are also almost all Nobel Prizes in biology or chemistry, all using X-rays to determine 3D structures with very complex systems. You know, they might have 3 million atoms, and they actually know where each of these atoms is to within, you know, a few angstroms by doing X-ray crystallography. And that is just a huge thing, and it takes up some fair fraction of the synchrotron ring at Argonne. Now, it turns out to celebrate this, in 2014, there was the International Year of Crystallography. And this was put out by Pierre's nemesis. This was put out by Nature magazine. But it's a very nice thing. And it has a milestone timeline of all the different things that are contributing to crystallography. The very last thing on this list, interestingly enough, is the X-ray free electron laser. And the milestone that we put on for the X-ray free electron laser was this here. And this is milestone 25, seeing in a flash. And this little picture has to do with this very large collaboration headed by Jana Schroedu at the University of Uppsala, where he wanted to make a 3D image of something that wasn't a crystal. It was just, this turned out to be a mini-virus. And that's what they think is the next step, because the big bottleneck in all these crystallography things is actually making a good enough crystal to diffract from. And so if you can get away from that necessity, it's a big thing. So, you know, this is what they think. Now, this is actually how you do that, right? This is the poster child experiment that was that's been bandied about for some time. And the idea is you take this big molecule and you drop it into this very intense X-ray beam, And scattering from this big molecule is captured, both in wide angle and in small angle. And from capturing all of the photons, from that, you can then come back and reconstruct a 3D structure. That's kind of the dream. For an AMO experimentalist, there might be like one or two in the room. For an AMO experimentalist, they might think, oh, this is just like the experiment I do in my lab, right? I may not take a big protein molecule, but I would take maybe a smaller molecule and I'd subject it to some laser. Maybe it's not X-ray, it's some laser, and then we'd catch all the fragments and figure out what's going on. So, in fact, of course, there's a lot going on if you take 1 trillion photons and focus it down onto this molecule that might only be a few nanometers in diameter. And so from an AMO perspective, there are these pretty interesting questions, right? So this was the simulation by Jan Schweiger's group that got everyone excited back in the year 2000. And this is a very famous diffraction pattern. And he simulated what would happen if you took those X-rays and blasted it onto a lysosine molecule with this type of intensity, 3 times 10 to the 12 X-rays, focused down to a 100 nanometer spot at 12 kilovolts, which would give you something on the order of 10 to the 22 watts per square centimeter. Like, this is a huge number, right? I mean, we listened to Lars and he was saying, okay, 10 to 14, 10 to 14, but this is just a big number, right? So it's interesting not only for the biologists, but it's also interesting for AMO folks. And so one would like to understand, so this is during the pulse. Before the pulse hits, it looks intact, and then during the pulse, it's pretty much intact for 10 femtoseconds. But after 50 femtoseconds, things are still on exploding, going all over the place. So, from our perspective, it would be interesting to understand this Coulomb explosion. And of course, prior to the Coulomb explosion, the electrons are running around all over the place inside this molecule. And the electrons are the thing that are actually scattering the X-rays. So that whole pattern is determined by where all the electrons are in this big soup. And so, it's also of interest for us to know that. And so we spent a lot of time on atoms just figuring out what was going on with that. And also the behavior at, this very high intensity. There are other interesting questions that I won't get into in this talk, but later. So, of course, so these things are big. They're accelerator-based. They cost on the order of $1 billion. I'll show you a little later. But of course, you don't do it just because of biology, right? So there was a whole science case made, the LCLS first experiments, from atomic molecular and optical physics, all the way down to soft X-ray material science and materials in extreme conditions. But the thing that the AMO community wanted to do was basically to understand and control, X-ray atom molecule interactions at these very high densities. And these, we would hope, would be a foundation for other applications, and also to provide diagnostics for the LCLS. Now, it also turns out that the LCLS was quite successful, when it first came out. And these X-ray free electron lasers, they're really proliferating. This table comes more or less from a new review of Modern Physics article that talks about the first 5 years at LCLS. And what you can see here is that here's the LCLS, and it was really the first one operating in the hard X-ray range. And the other one that's operating presently is this one in Japan, SACO, which also operates in the hard X-ray range. And then there are these softer X-ray facilities in Germany with Flash. But what I want to say is that the X-FEL output spans a very large photon energy range. And this focus intensity gets quite large. But if you look over here, this is when these new things are coming up. They're coming up in the next couple of years. There are 15 different innovations coming up, which is going to vastly multiply the opportunities to do things. And so this is just to try to make a little bit of connection back to what you've been listening to for the rest of the day. And this is actually from a review article that Margaret wrote in Science just of this year. And it compares these accelerator-based sources with the laser-based HHG. And over here, on this side, are the accelerator-based sources. These are big things. These are billion-dollar things, right? And then over on, and what it shows as a function of time, and this is the X-ray brilliance, which you know, for people, it's a quantity that everyone uses. It's the photons per second per 10% bandwidth per millimeter squared per milliradian squared. And you can see it's going up exponentially. And this is the jump from the synchrotrons up to the FELs. Turns out, and you know, this shows maybe a 4-order of magnitude jump. But in fact, if you plotted peak brilliance rather than average brilliance, this jump would be 9 orders of magnitude. I mean, it's huge.
So
and over on this side,
Linda, is this the Moore's law for X-ray?
Pardon me?
Is this the Moore's law for X-ray radiation?
Yes, yes, yes. You know, it's very interesting. I have a slide which is not in this deck, but it compares Moore's law to X-ray brightness, and of course, X-ray brightness wins by a lot.
Yeah, it seems to be orders.
And over here, you know, we have the laser-based HAQ, which can get way down into these very, very fast. You know,
But I have one more question.
Yeah, yeah.
Is it getting cheaper?
Is it getting cheaper?
Per photon.
Okay, let me say one thing. I will say that the people who are coming later, I was just recently in Switzerland, they are building a Swiss bell. Theirs is significantly cheaper because they figured out ways to make things a little bit more compact than otherwise. And of course, it's made with Swiss precision, right? So you know, people do learn from what has been done before. So, but it's not quite like, you know, computing power in your iPhone. But
They
no.
don't get smaller.
Okay. Yeah. You know, and high harmonic-based sources are less expensive than $1 billion. Is that right, Margaret? Yes, less. And much more convenient. You go to much faster timescales, but they don't quite produce the amount of X-rays per pulse, per bandwidth to do some of these things that these sources do. So what, you know, for this particular conference, it's like, okay, this is ultra strong radiation at ultra short wavelengths, and so that's kind of what we're doing here. Okay, and so just this is you've seen it many times already before, but you know, at these long wavelengths, you have these laser-driven processes that can be described by classical trajectories after it's been released, and we've heard all about it. But what I want to say is now here at the LCLS at these X-ray wavelengths, you have huge powers, like 100 petawatts per square centimeter. But upon remotive energy, this energy in the field, and you know, this displacement is nicely shown by one of Paul's graphics, is really small compared to what you have in the optical regime. It's just very, very different, right? So there aren't really any field-driven processes that are happening here. And so then I thought, oh, well, what about, you know, this Keldysh parameter that everyone is talking about? Okay, so this is this picture that we heard this beautiful lecture by Lars about, right? And so the tunneling time of the laser period is this Keldysh parameter, and you can calculate it by, you know, known quantities of the field that you're putting on and the properties of your system. And if you can get this thing below 1, then you have some good chance of tunneling in the very naive, whatever, experimentalist perspective. And so, you know, when you have X-rays, well, you're over many ionization potentials, right? So you just directly ionize. And I already told you that you hardly have any field-driven processes. But it's kind of interesting, actually. If you look at hydrogen, and you look at a 1 micron laser, and you have your 10 to the 15 mots per square centimeter, you get this, you know, lowish Keldysh parameter. But if you just scale up by, you know, a factor of 10, and you look at hydrogenic neon, and then, you know, it has an ionization potential of about 1,000 eV, and you go with, like, you know, 100 eV photon, and it's also a 10 photon process. It's a very similar thing, actually. And then, you know, at 10 to the 21, remember I was telling you about 10 to the 22 before, now you're getting into the same bizarro regime. And maybe this doesn't work. I mean, Lars would have to tell me it doesn't work, but well, it's not as if you have hydrogenic neon sitting around to play with either. So, you know, but I will tell you that you will see that we can produce hydrogenic neon. So what's going on with the X-FELs, right? What's going on is that basically they can saturate single photon absorption. And so a typical synchrotron pulse, that you use around the ring might have about 10 to the 6 photons, and you might focus it down to square micron or so. And for argon at 6 keV, you have sort of this cross section. So the probability of absorption is cross section times the fluence, and that's on the order of 10 to the minus 6. So it's a very small probability. But in the X wells, you have 10 to the 12 photons per pulse can easily be focused down to 9. So you can easily saturate that. And so you can define a saturation parameter for the fluids where all these things start to happen. And you can actually describe what's going on in an atom with a rate equation model where you simply calculate what these cross sections are for all these different processes, and you track what's going on in each of the states. And so that turns out to work very well. And so that's quite simple. Now, the one photon processes have caused this proliferation of synchrotrons around the world. Like, it's not just at Argonne that you have a synchrotron. You have them everywhere because they're very useful. If you go to this website, lightsources.org, you can do a tour of all these different ones. So let me just quickly tell you what's going on, in the one photon limit that cause these things to be so interesting. So fundamentally, there are a number of processes in this photon energy range between a kilovolt and say 100 kilovolts. The dominant one, this is a picture for carbon. The cross section for photoabsorption, which is this big thing, is completely dominant. There's a cross section for coherent scattering, which is elastic scattering, which is what's used for the crystallography. And then there's also, for incoherent or Compton scattering, and then these other things that happen in the nucleus that are at much higher energies. But let's focus in on photoabsorption. And so photoabsorption, if you come out here at some particular energy, what you see is that if you get above the threshold, you eject 1s electron. But it's not as if you don't talk to the other guys at all. They're also there. You can actually dissect this photoabsorption cross-section into all the partial cross-sections. And this was done way before synchrotrons. This is done with like an X-ray tube and photoelectron spectroscopy, because of course for each one of these shells, you know exactly what the electron energy should be coming out from each. And there are lots of details associated with this too, which people have discerned over the years, because not only can you have photoabsorption, but you can have things where electron correlation can play a role, and then you can have not only a single 2s electron come out, but you can also do some excitation or double ionization. So there are many things that can actually happen when you hit an X-ray onto an atom. And it turns out that you have one of the experts on all of this in the room, sitting in the front row here, because Tony knows all. He's written a very long review article on this many years ago. But if you need questions answered on it, he's your man. So then what happens after photoabsorption? Well, there are two things. You create a hole down here. That hole can be refilled either by X-ray fluorescence or it can be refilled by Auger processes. The two have sort of different selection rules and operators and behave quite differently as a function of Z, but it's very well known. So at the low Z range, K shell Auger is the dominant process. When you get up to high Z's, fluorescence is dominating. You can find all of these energies, all of these fluorescent lines out there in the literature and on XCOM, and they're very easy to find, and people use them all the time. So what you can do with this is if you have these X-ray emission lines, they're very characteristic for elemental identification. And so what you can do, if you go back to this X-ray imaging, is that you can take your X-rays and you can shine it onto your sample. You can rotate your sample around, and you can collect all of the X-rays that come out from there. And then what you can do is, each element lights up its own color. And so if you have a dispersive detector, you can tell exactly where each element is. And so this was a very nice demonstration done at Argonne that shows the 3D elemental distribution in a diatom. So this thing was, I guess, a few microns in diameter, and they could do like 150 nanometer voxels. And you can see here, this I think is silicon, and then they have iron and magnesium. And you can really see how that thing was made. I think it's quite pretty, actually.
So how many atoms do they have roughly in this sample?
In this diatom,
Yeah,
I couldn't tell you for sure.
no, but roughly.
But let's see, it's 3 micron, it's probably 10 microns in diameter, so it's might be a 10 micron sphere. And so if you have a 10 micron sphere and everything's, you can calculate from that. So if it's by an angstrom, right, that's 10 to the minus 10,
Right.
10 to the minus 6, 10 to the 4, 10 to the 12, I guess. Right.
Do they do this with biological molecules too?
Hmm?
Do they do this with biological?
So I guess I could call this a biological molecule. This is a diatom that's found in the sea, and they fished it out, and
But I mean, 10 to the, I believe you 10 to the 12. I mean, that's a lot of atoms, right?
Oh yeah.
I do 1 atom.
Okay.
And you have, how can you actually fight your way through all the information that you have in this diffraction?
Oh, this is not a diffraction at all. All this is.
Oh, it's just absorption?
This is fluorescence,
Oh,
right?
fluorescence,
So
yeah.
you shine your X-rays onto your sample.
But even
And
then,
all
I
they-
mean, you have this huge amount of information coming out, right?
Well, okay, so this is done at a synchrotron, and you have a dispersive X-ray detector here. So it can discriminate, an X-ray that it sees from silicon from one that it sees from iron. So all you need is, an energy detector that can distinguish all these different elemental X-rays. And so then you rotate it around like you do normally with tomography, and then you can gather all your information.
You're 10 to the 12
Yeah.
points.
Well, you can see it at these 150 nanometer voxel ranges.
Oh, I
So
see.
in the 150 nanometer voxel, you will have, some
I see,
number of
so
atoms,
it's not,
right?
so the resolution.
So you don't see one atom.
Right, okay.
This is not atomic resolution, but it's still,
I'm sorry, I
for
misunderstood.
biology, it's pretty interesting,
I
right?
misunderstood, sorry.
And so, well, I mean, I will say that, this whole group that's doing this is really excited about the APS upgrade, because the upgrade is going to increase the flux that they can put on this sample by about a factor of 100. And so it took them a long time, it took them weeks to do this particular demonstration. And so, they're very excited about that. Okay, and so then, there are all these X-ray spectroscopies. I'm not going to explain them to you. Books have been written about it. But it turns out if you take the X-ray absorption spectrum, you can get a lot of information even on simple molecules, right? So you can get distances to neighboring atoms if you have a central absorbing atom. From the near edge structure, you can get the oxidation state, geometry, coordination environment, and so on and so forth. Because what this near edge structure is doing is probing the first unoccupied levels in your system. And of course, from photoelectron spectroscopy, you get energy levels of all kinds of things. This molecule is particularly, I think this molecule is particularly cool. It's a chi-C1 molecule. And so what you see is there are all these different carbons in this molecule. And you can see from the photoelectron spectrum that this carbon has, with all these F's on it, has, a chemical shift over here, where with all the H's is over here. They're very, very distinct. So you can really tell the difference, from one atom to another. You can imagine, yeah, that's right. Right, you could excite something over here, and maybe you could see what happened over on the, I mean, it's just a very nice demonstration molecule. Okay, so now, ultra-intense X-ray interactions with atoms, right? So I want to tell you a little bit about this Linux coherent light source. And it's just because, I was around when it was first coming up, and so it was very interesting, so I can tell you these stories, and sometimes it's nice, and it's after dinner, all this other kind of stuff. But, okay, so this thing, this XBEL was based on an idea of Claudio Pellegrini in 1992. He got the Lawrence Award for this year. And it's really cool because they got to use the last 1 kilometer of this existing 3 kilometer LINAC, so put that high energy physics machine, which was a little bit out of date, into good use. And it would accelerate electrons up to roughly the speed of light, 14 GeV. It would send it through an undulator hall, which is a periodic array of magnets about 100 meters long. and it'd be transported, yeah, go back, to, the near experimental hall where we do experiments, or the far experimental hall where other folks would be doing things. And it was a collaboration of many, many labs. But it was so exciting when this thing lays for the first time at 1.5 angstrom back in 2009. And I want to quote this from John Galida because he was also the person who built the Argonne APS. So then he went over to Stanford and did this, and he goes, okay, in my life before SLAC, I had the privilege to participate in various capacities in the design, construction, and commissioning of 2 Linux, 2 synchrotrons, 4 storage rings, 3 FDLs, and now I've had the privilege to be in SLAC's main control room on April 10th when the Linux coherent light source became a 1.5 angstrom laser. I don't expect I will ever, as long as I live, see such a beautiful, smooth turn-on of any light source. With each undulator placed on the beam path, the FDL power increased by a factor of 2.3. 2 hours into the first attempt at blazing, the pinpoint of FDL light from 12 undulators was nearly 2,000-fold more intense than plain old undulator radiation. The team called it quits at 11 p.m. that night, and when they returned at 8 a.m. the next morning, the FDL light came back as soon as the shutter was open. And so you can see, the difference before it was lasing when they put in enough undulators. I mean, he was very excited, and so he shows, he even smiles sometimes. And so this is John Galida, and this is Paul Emma, who was sort of the master machine builder, steerer. And this is Jerome Wong, who's now sort of their head of accelerator operations. And they're all still there for LCLS2, which is great, because they clearly know how to make things work. I just wanted to show you this because, of course, from Argonne, we're very proud that we actually made these, all of these undulators. And, there are lots of undulators, and they're on ramps, and you can stick them in one at a time. And so you can watch as you start to stick in these undulators, the saturation of the lasing output. And it shows, after about 60 meters that the whole thing is saturated. So you can just keep putting them in. And so it's kind of cool. So what's actually coming out the end after you do all this? Well, it's not quite as pretty as the lasers that you probably have in your lab or are used to. But the electron bunch comes in, it goes through these undulators. As it goes through, the electrons self-organize, and then they have transistors, and out comes a self-amplified spontaneous emission pulse. This pulse is rather noisy, both in time and in spectrum, but it has a lot of photons. And typically, one has a bandwidth on the order of a half-ish% or so coming out the end, and a duration that's tunable between, say, 10 and 100 seconds, and very short spikes, but quite a bit of energy. Turns out you can tune this radiation if you change the undulators as you would do with any source. So I want to just tell you a little bit about our first experiment because it's kind of cool how much you can learn from just doing something really simple. And so we wanted to investigate the nature of electronic response, and we took these, affluence of about 10 to the 5 X-rays per square angstrom. Turned out that on just the day before we started our experiment, that Paul Emma, that I pointed out to you before, we had this little meeting, and there were like 20 of us in the room or so, and he said, hey, Linda, do you think, would it be interesting to you if we could actually change the duration of the pulse? And I said, well, of course, right? How long will that take? He said, oh, maybe about 30 minutes. He said, how do you do that? He said, well, we just change the bunch compressors. I said, well, we have to do that, right? You have to have all the knowledge you can, especially when you're doing something very simple. And so we were able to change the pulse durations there. And then the initial energy range that was advertised was 800 to 2,000 dBm, and we could get on this order of power. But it's kind of far from these original specs of 10 to the 22. But so our approach was to use a very simple atom, neon. It had, all the binding energies. I showed you all those other things that you know about it. We know that when you do intershell excitation, you have an OJ yield on the order of 98%. And the OJ clock, the time that happens, is on the order of 2.4 femtoseconds. So we figured, okay, We can go between 800 and 2000 eV. All right, this is really good for neon. It has an edge at 870. That means we can probe the changes in interactions with